In this video, we're going to see what a derivative of a function is. If you go back to the video on lines and slopes, you'll recall that if we have a linear function f, the slope of that line we described as being the value of f at x2 minus the value of f at x1 divided by the difference between x2 and x1. How far apart x1 and x2 were didn't matter. Pick any x1 and pick any x2, you just needed two values of x, and you would be able to calculate the slope of that line. What if f isn't linear? If f isn't linear, how do you describe the slope of a curve? Well, we're going to do the same thing. We're going to look at the difference between the value of f at 2 points, x1 and x2, except we're going to insist that x1 and x2 be really close to each other. So let's suppose the difference between x1 and x2 is just some number h. x1 is just x, x2 is x plus h. So we've got f of x2 minus f of x1 divided by x2 minus x1. Again, x2 is x plus h and x2 is just x. We'll notice here that the x and the x are going to cancel in the denominator. So we just get the difference between the value of f at x plus h and the value of f at x. And we divide that by the amount by which we change x. If we have x here and x plus h here, and the value were this much, so we've got this point on our curve, and perhaps f of x plus h would be this much. So if you were to draw a straight line that goes through these two, the slope of that line would be exactly this. Remember, it's rise over run. How much does the value rise? It's the difference between f of x plus h and f of x. And how much does it increase? By h. And that's exactly what we've written down here. Remember that I told you that we wanted a really small h. So what we're going to do is take the limit as h goes to 0 of this ratio. Don't let the limit scare you. We're not going to deal with sequences in this course, but technically what we're looking at is the limit. We're just taking h to be really close to 0 without being 0. This ratio is what we're going to represent by df dx at the value x. And that's what we call the derivative of a function. So the derivative of f is df dx. And let's look at a graphical representation of what this is. Here we've got a function f, which is this guy over here. So let's take some x, and we want to know what the derivative is at x. Well, take some h. So we look at x plus h, and we look at x, and we're going to calculate the value of the function at each of those. So the value of f at x is this much. The value of f at x plus h is this much. So we are going to then look at this point here. So x, f of x, and we're going to look at this point x plus h, f of x plus h. We get this point right here. So if we were to draw a hypothetical line between the two, the slope would be f of x plus h minus f of x divided by h. So it would be the slope of this line. Let's try and make h a little bit smaller. Now we've got the slope of this line. And we're going to keep going until h is so small that we can barely distinguish between x and x plus h. And that's when we're going to end up with this line here. And that line is what we call a tangent to the curve of f of x. So the curve of f of x is given by this, and this line, it just barely touches the curve of f of x at this point right here. And so we call this blue line the tangent, and the slope of that line is what we've defined to be the derivative. So if we look at this line and we move to the right by 1, the height of the line changes by the derivative of f at x. Remember that the derivative depends on x. If we were to look at a different point here, let's call it x prime, the tangent line would be like so. And so the slope of this line is different from the slope of this line. So the derivative of this function f is different at different values of x. In other words, it depends on x. It's nice to understand what derivatives are in this geometric way, but we still need to be able to calculate derivatives without resorting to graphs and tangents. So here are some basic rules for how to calculate derivatives. The first rule I'll give you is for a constant function. So you just have the function f of x equal to c, where c is some constant. So for instance, f of x equals 3, f of x equals pi, whatever constant. The derivative of f of x is 0, because if we were to draw a graph where we put x on the horizontal axis and the value of f of x on the vertical axis, no matter what x is, if we look at that constant c, f of x is going to be exactly c. So you've got a horizontal line. What is the slope of a horizontal line? It's 0. And that's why df dx at any x is going to be 0 for a constant function f. What about a function that is the sum of two different functions? So we have some function g and we have some function h, and f of x is their sum. The rule for calculating the derivative of f is simply to take the derivatives of g and h respectively and add them together. What if f is the product of g and h? So for every x, f of x is g of x times h of x. In that case, you're going to follow the multiplication rule. The derivative of f at x is the derivative of g times h plus the derivative of h times g. Another really useful rule for the kinds of calculations we'll do is the power rule. So let's say you have f of x is a times x to the b, where a and b are both constants. So for example, you have f of x equals 5 times x to the 3. In this case, a would be 5 and b would be 3. There's a simple rule you follow to calculate the derivative. So you leave the a fixed, then you decrease the exponent by 1, and you multiply by the exponent as well. So the b goes here, and here we just decrease it by 1. Think of it as just taking one of these b's, putting it here, and then you're left with b minus 1. So that's the rule if you have an exponent. Another type of function that we often use are logarithms. The derivative of log of x is just 1 over x. Now this one's going to look a little bit complicated, but it's going to be very useful. Oftentimes we're going to have f of x being the function of some function of x. So for example, you might have f of x equals log of the square root of x. So in this case, h of x would be the square root of x, and g of x would be the log of x. So if we apply g to h, we have f of x. How do you take the derivative of this? Start inside out. So start from the inside and move out. You take the derivative of h, then you take the derivative of g with respect to its argument. So in this case, dg dx would be 1 over x. But you don't evaluate this derivative at x, but rather at h of x. So in this case, you have dg of square root of x with respect to square root of x. What we're doing is we're treating the variable to be square root of x rather than x. So that's going to be 1 over square root of x. H of x in this case is x to the 1/2. That's what the square root is. So dh dx is using the exponent rule. A is 1 because we're not multiplying x to the b by anything. B is 1/2. So we put 1/2 x to the minus 1/2. Remember, x to the minus 1/2 is 1 over x to the 1/2, or in other words, 1 over square root of x. Putting this together, using the chain rule, we get df dx is this thing, 1 over square root of x, times the derivative of h with respect to x, which we saw is 1 over 2 times 1 over square root of x. We've got two square roots. Multiply those together, we get x, so we get 1 over 2x. Between the chain rule, the multiplication rule, and the addition rule, you can now put things together, and you can use them as building blocks to take the derivatives of more complicated functions. So let's work through this example where f of x is 5 times x to the 4th plus x log x. Right away we see that we can use the addition rule because we've got the sum of two different functions of x. So we're going to let g of x be 5 times x to the 4, and we're going to let h of x be x log x. So the first task is to calculate the derivative of g of x, which is 5 times x to the 4th. So this is of the form a x to the b. So remember, the derivative of that is a times b x to the b minus 1. Here a is 5, b is 4, so we've got 5 times 4, a times b, times x to the 4 minus 1. That's 3. So we've got 20 x cubed. What about h of x? We need to take the derivative of this. But here we see that it's the product of two things. It's a product of, we'll call it g prime and h prime, where g prime of x is just x, h prime of x is log x. We're going to appeal here to the product rule. Remember that the product rule is going to tell us that dh dx x is, take the derivative of g prime. Remember, it's the product of g prime and h prime. So take the derivative of g prime with respect to x, evaluated at x, times h of x, plus take the derivative of the other one, dh prime of x, dx, multiplied by g prime of x. Again, g prime of x is x and h prime of x is log x. Easy enough to see that the derivative of this with respect to x is just 1. To use this product rule, we still need to calculate dh prime of x, dx. But it's simply the log, so it's just 1 over x. So now we have all the components we need to use the product rule to find the derivative of h. dg prime of x is just 1. dh prime of x is 1 over x. So the product rule, remember, tells us that we take the derivative of g prime with respect to x and multiply it by h prime, and we take the derivative of h prime and multiply it by g prime. And we know what all these pieces are. This is 1, this is log x, this is x, this is 1 over x. X and the 1 over x cancel to give us 1. 1 times log x is just log x. So the derivative of h with respect to x is just log x plus 1. Finally, we know that the derivative of g with respect to x is 20x cubed. The derivative of h with respect to x is log x plus 1. So we can use the addition rule. The derivative of f, which is the sum of g and h, is just the sum of the derivatives of g and h. So we've got the derivative of g with respect to x is 20x cubed. The derivative of h with respect to x is log x plus 1. So this is the derivative of f with respect to x. Let's look at one more example. F of x is 1/3 x minus a half cubed. Here we've got a function of x. So let's suppose we take a function g, which takes some argument. In this case, I've written it as y, but it takes some argument y and returns 1/3 y cubed. And we have a function h that takes x and gives us x minus a half. Let's remember what the chain rule says. df dx at x is the derivative of g with respect to its argument, which is h of x, evaluated of h of x, times the derivative of h with respect to its argument x, evaluated at x. So we need to calculate the derivative of g, and we need to calculate the derivative of h. Let's look at this. What's the derivative of g with respect to its argument, which I've represented by y? These are arguments, these are variables, so you can call them anything you want. We're going to use the power rule here. We've got a times y to the b. The power rule is the same whether you call it x or y. So the derivative of this with respect to y is a times b, y to the b minus 1. Here a is 1/3, b is 3, so we get 1/3 times 3 times y to the 3 minus 1. 3 and the 3 cancel out, so we get 1 times y to the 3 minus 1, which is 2, which is just y squared. And that's what I've written down here. So we have the derivative of g with respect to its argument is just the square of its argument. Let's look at this guy. The derivative of x minus a half, the derivative of just 1. You could use here the addition rule, take the derivative of x, plus the derivative of minus half. But you could also recognize that this is a linear function, and the slope, which is the coefficient of x, is just 1. And so that's the derivative of h. So now we can use the chain rule. The derivative of f with respect to x, remember we start inside out. We take the derivative of h with respect to x, which is just 1, times the derivative of g with respect to its argument, evaluated at h of x. The derivative of g with respect to its argument is just the square of its argument. And if we're evaluating it at h of x, we just substitute h of x for y. So we get h of x squared. But we know what h of x is. H of x is x minus a half. So as you can see, using the basic building blocks that I gave you for how to take derivatives of functions, you'll be able to take the derivatives of far more complicated functions like this one, or the earlier example. We're going to find that being able to take derivatives is going to be useful for things like optimization, as you'll see in one of the later videos.